Okay, hi. So this is another tutorial here. This is work and energy problems, problem D for potential energy. Now, there are 10 problems that are associated with this particular worksheet that I gave you guys. Um, Now, what I want to look at is question number 10, because there is kind of a little wrench that was thrown into this. Okay, okay. So as I'm looking at this, here. We've got problem 10 right here, and this is the one that I'm going to do for the tutorial. The problem is that they have something called elastic potential energy that's in here, which we did talk about it, but I never really gave you guys an equation for it. Okay, so when April Moon set the record for flight shooting in 1981, the arrow traveled a distance of 9.50 times 10 to the 2 meters. Suppose the arrow had a mass of 65 grams and that the angle at which the arrow was launched was 45 degrees above the horizontal. Okay, part A is asking here about the kinetic energy of the arrow as it was at the instant that it left the bowstring. Okay, that's fine. We can do that. Okay. Part B here is asking about if the bowstring is pulled back 55 centimeters uh, from its relaxed position, then what's the spring constant? Well, that's the problem. That's the part where we have the problem. Okay, so I'll go through that and show you how to do that. And then we have, assuming that the air resistance is negligible, determine the maximum height. This is fine because this uses gravitational potential energy, so we're okay with that one. Okay, so it's just that part B that we're going to have a problem with. All right, so let me start off here and let's get all of our givens going and stuff like that. So we got problem number 10, okay, and problem number 10, we're given mass, and the mass of the object is 65.0 grams, and we need it in kilograms, so that's going to go to, and that'll be 0.065 kilograms. Okay. Then the distance that it travels, which we'll call dx, that's the distance in the x direction, is 9.50 times 10 to the 2 meters. Okay. And then lastly, we have an angle theta, which is 45.0 degrees above the horizontal. Okay. Now, let's look at this. What we're looking at is an arrow being shot. Okay, so here's my arrow right there. It's being shot at an angle of 45 degrees, like that. Being shot at the angle of 45 degrees. All right, so as it travels, it's going to go up, and then it's going to get to its maximum height, and then it's going to start traveling back down, and then when it comes back down here, it's going to come in 45 degrees. Okay, oops, do it right there, 45 degrees, boom, right there. So this guy will come in there and then down there. Okay, try to make that parabola as best I can. All right. So a little tiny mess up, but that's okay. All right. So this angle right here is 45 degrees. That's our theta. Okay. Now keep in mind that this is projectile motion. What we're looking for is kinetic energy. So kinetic energy as it's being released is the same equation for kinetic energy that we always have, which is 1/2 mv squared. So we're going to be going back to 1/2 mv squared once we figure out what the v is. Okay. Now remember, this is our v right there. Okay. That's that velocity that is being released at. Okay. So this is a projectile. So remember, we have a component that's going this way. That's our Vx. And then we have a component that is going this way. And that's going to be our Vy. Okay. So we now need to figure out what those are because we've got to put those together to figure this out. All right. So how do we figure out velocity in the x direction? Vx. Well, Vx is dx over t. That is in your equation sheet, okay? Dx over t. But there's another way to figure out Vx, and that is using vectors. That is also V cosine theta. Cosine theta because it's the adjacent side. Okay, so we're going to use both of these. So the next thing we're going to look at is our Vy. Okay, so Vy is going to be kind of similar to this. We're going to take Vy and we're going to say that Vy is g times t, gravity times time. But the time we're using is not this time. Okay, so that's going to be time over 2. Remember, it's half the amount of time that it took to get here. Remember, it said that um, air resistance was negligible, so we're not going to include our air resistance. Okay, so what I'm going to do is I'm going to solve this top equation here for time. So time equals dx over v cosine theta. I forgot to mention here, same thing that we did right in this area, is that this guy here is going to be equal to v sine theta. So I'm going to take my t, since I solved for t here, I'm going to take this t and I'm going to plug this t into this t here. Okay. So when I do that, the 2 stays in the bottom, which goes with these guys in the bottom. The dx stays in the top, which goes with the g. Okay. So what I end up with here is a new equation that's going to look like this. Okay. V sine theta equals g dx divided by 2 cosine theta cosine theta. Okay. V cosine theta, sorry. I was jumping ahead of when I started writing that other piece down. Okay. So now what I'm going to do is I'm going to take the V here, and I'm going to move it up to the top. I'm going to take the sine theta and move it down here. But what do I get when I have V times V? That equals a V squared. So I still have G dx divided by 2 cosine theta sine theta. So now we put in our numbers, and to get this, we're going to end up doing a square root. Okay. So V equals, we're going to start the square root here. I don't know how long it's going to last, so I'm not going to put the top on it yet. So this is going to be 9.8 meters per second squared times our dx, which was 950. Okay, 9.50 times 10 to the 2 meters divided by 2 cosine of 45 degrees sine 45 degrees. And then I'm going to close up my square root there. Okay, and then what this all equals is right there. So I'm going to take out my handy dandy calculator. And the calculator is getting low on battery here. My phone is. Okay. So what we're going to do here is we're going to do square root, and I'm going to put in the extra. I'm going to put in the extra parentheses, okay? And I'm going to do 9.8 times 950, because that's what that guy is right there. Close my parentheses. I'm going to divide by, and I'm going to start with the parentheses. I'm going to say 2 times cosine 45, close parentheses, times sine of 45, close close the parentheses once. That closing once gets this guy. Then I got to get this outer guy here. Close that one. And then I got to get the very outer one there. Equals. And that equals 96.5 meters per second. So now I'm going to take 96.5 and I'm going to put it into this equation back up here. So kinetic energy equals 1/2 times our mass, 0.065 kilograms, times 96.5 meters per second quantity squared. And that's going to be my kinetic energy for when this bow is released, when the bow releases the arrow. Okay, so clear 0.5 times 0.065 times 96.5 quantity squared equals, and that's, oh, I did think I did 65 instead. Okay, so 0.5 times 0.065 times 96.5 quantity squared. There we go, that's the number I want. Okay, so 303, we're going to round, 303 joules. So kinetic energy equals 303 joules. Okay, that's my answer for part A. Okay, so let's label that A right here. All right, close this off right here, and then we're going to do B. Well, the distance that the bow was pulled back was 55 centimeters. So I'm going to call that X, and the reason I'm going to call it X is because that's what it's called. Okay, so this was 55.0 centimeters, and that's going to go to 0.55 meters. Okay. Now, all of this kinetic energy came from all of the potential energy. So basically what we're looking at is the change in potential energy is equal to the change in kinetic energy. But the change in potential energy is elastic potential energy, and the elastic potential energy went from 0 to something. Okay, so this is just going to be potential energy equals the kinetic energy. This is the total kinetic energy. So that's going to be the change in kinetic energy that we have here. Okay. All right, so what is elastic potential energy? It is 1/2 kx squared. It looks very familiar to 1/2 mv squared, but it's not. It's not the same thing. Okay, k is what we call a spring constant, and the spring constant is how much every individual spring, rubber band, bowstring, whatever, snaps back, the way that it snaps back. X is the distance that it's pulled, and it could be in any direction. It doesn't have to be at X, but that's the way that they labeled it. All right, so what we're looking for here is K. So I'm going to move it over here. I'm going to say K is equal to, well, I got to get rid of the half. So that means I'm going to multiply by 2. So it's going to be 2ke, 2 kinetic energies. And then since I'm looking for this guy right here, I need to divide by x squared. Divide by x squared. So that means that K is going to be equal to 2 times 303 joules divided by 0.55 meters squared. So the constant here is going to be it's going to be 606, and that's 2 times 303, so 606 divided by 0.55 quantity squared equals. Okay. And we get 2003. Now this is going to be newtons per meter, Like I said, we didn't really talk about it. I'm not going to test you on this, but problem number 9 does use this. So in problem number 9, you will need to use this particular number. Okay. All right. Now the last problem, this is the problem that I wanted to get to because this is about potential energy. So problem C. All right, there are no givens that are in here, but what we're talking about in this problem here is that when we are looking at the projectile motion, okay, we have down here at the bottom, this here is representing total kinetic energy. So this is going to be kinetic energy total, but it's kinetic energy at the bottom. So I'm going to call it bottom. Okay. When it gets up to here at the top, okay, notice which way is the kinetic energy going? Well, the kinetic energy is no longer going at that angle, it's going this way. It's horizontal. So the shift here is in the angle that's there. Okay. So up here at the top, this top portion is going to be potential energy. So potential energy, and that's going to be at the top. But then we're going to also add to it the kinetic energy at the top as well. But this kinetic energy at the top, that has got to be affected by the cosine of 45 degrees. Okay, so let's get back down here to where the calculation's going to go. I'll use blue on this one here because we're going to have kinetic energy at the bottom is going to be equal to potential energy at the top, which is mgh, plus the kinetic energy at the top. Now, kinetic energy at the top is going to be equal to, well, our kinetic energy, 1/2 mv squared. But the v is going to be v cosine theta. It's because that cosine theta, we have to get that angle right, okay? We got to put it back down to its horizontal direction, okay? So when I'm looking at my potential energy here, my potential energy at the top is going to be equal to my kinetic energy at the bottom minus my kinetic energy at the top. Okay, so I'll put that in there afterwards. Okay, but potential energy is mgh equals kinetic energy at the bottom. Now, kinetic energy at the bottom, I'm not worried about because I solved it up here at the top. Okay, so I solved it right here. That's my kinetic energy at the top, or at the bottom. Okay. Minus kinetic energy top. So what I'm looking for is H. H is going to be kinetic energy at the bottom minus kinetic energy at the top divided by mg. Okay, so that's how I'm going to solve this particular problem. But I've got to solve this first. Okay. So what we're going to do here, it's not too difficult. Kinetic energy at the top is going to be 1/2 of 0.065. Then I'm going to multiply this by 96.5 squared cosine of 45. I'm going to put another set of parentheses here because that's got a square also because it's part of the velocity. So it's got a square too. If you don't square it, you're not going to get the right answer. Okay. So my kinetic energy at the top is going to be equal to, now I'll take out my handy dandy calculator. I have to use this twice. Here. Okay, so I'm going to go 0.5 times. Okay. 0.065 times 96.5 quantity squared times, now I got to use parentheses, okay, cosine of 45, close my parentheses, I got to close it one more time because I need to square this entire thing, okay, equals. So that's going to be 151 joules. Now I'm going to place it in here. So my height is going to be 303 joules minus 151 joules divided by 0.065 times 9.8. So my height is going to be equal to, I close this off, and I see 303 minus 151, that equals 152, divided by, and I got to do my parentheses here, okay, 0.065 times 9.8, close parentheses, equals, and I get 239 meters. 239 meters. So that's how high that arrow will go. All right. Okay, so that is how we do that. This B portion is the elastic potential energy. So this is elastic potential energy equation right there. And so that you will need for problem number 9. Okay, also. All right. Okay, well, good luck with all the rest of them. And